At some point in the distant past, the ancestors of today's plants settled on a funny green molecule to help them make food using the sun's energy. We don't know exactly where this molecule came from, or why it was green. I mean, black would clearly be better at absorbing all colors of light. However, the fact that almost all plants on Earth are still using chlorophyll's recipe must mean there's more to it than meets the eye. Plants need light-absorbing molecules like chlorophyll to do just two things. 1, capture the sun's energy, and 2, transfer that energy to other components of the leaf so they have fuel to make sugar. It turns out that having light-absorbing molecules that are bad at absorbing certain wavelengths of light isn't actually that big of a deal, because molecules like chlorophyll aren't just on the surface of a leaf, but instead are spread in layers throughout. That gives the leaf ample opportunity to absorb every photon of light passing through. For example, even though molecules of chlorophyll are abysmal at absorbing green light, this layered arrangement allows a leaf to capture up to 80% of the green light that hits it. In fact, if a leaf were to absorb all that green light right at the surface, it could be at risk of taking in too much energy too quickly and suffering the botanical equivalent of sunburn. Another handy thing about capturing the energy in a spread-out fashion is that, once absorbed, the energy is already spread out. No need to transport it throughout the leaf. And that's good because now, the real work is about to begin, using the sun's energy to cook up sugar from water and carbon dioxide. And this is where chlorophyll really shines. Other cellular kitchens, like those in purple bacteria, can make sugar too, but not quite as well as the green ones. That's because the green sugar-making machinery is both smaller and thus less energy-intensive to build, and at the same time has a more powerful system for using light energy. It can combine the energy captured from 2 photons of light together to fuel a supersized sugar synthesis. So, among the light-harvesting systems that did evolve, the green recipe was superior to the purple one. And we can see the outcome of that competition every day all around us. I mean, green photosynthesis accounts for more than 99.9% of the natural productivity on Earth. But did the physics and chemistry of green make that outcome inevitable, or did it just turn out that way? Is there a planet somewhere out there in our galaxy dominated by purple plants? We don't know, but what we do know is that here on Earth, chlorophyll's strengths far outweigh its distaste for greens. And for our planet at least, maybe that's not such a bad thing.